Welcome to Study Loop.
If the particle is less than some critical radius, prove that it will be blown out of the solar system. So we can say that we are going to let r and rho be the radius and the density of the particle, respectively. We're going to treat the particle as a sphere. So we can first say that here, the force of gravity on this particle, let's start with part A, the force of gravity on this particle would be simply equal to the gravitational constant times the mass of the sun times the mass of the particle itself divided by r squared, where r squared would here be the distance between the particle and the sun. We're going to say that most of the force of gravity would come from the sun. This would be equal to the gravitational constant times the mass of the sun over r squared. And then here, we're going to multiply this by 4 pi r cubed divided by 3. This would be the volume of a sphere multiplied by rho, the density. This would essentially be equal to the mass of the particle. Now, we're going to say that if the P is the power output of the sun, then at the position of the particle, the radiation intensity I would be equal to the power output of the sun divided by 4 pi r squared, where again r is the distance between that particle and the sun. We can then say that the radiation pressure from the sun would be equal to I over the speed of light, or we can say the power output of the sun divided by 4 pi r squared times c, the speed of light. Now, all of the radiation that passes through a circle of radius r and a cross-sectional area of A equals pi r squared, the cross-sectional area of a circle. This would be essentially, we could say that this would be the force of the radiation pressure. This would be equal to the force of the radiation pressure itself multiplied by the cross-section of the part of. If we're treating the particle as a sphere, A would be equal to pi r squared. So essentially, this would be equal to pi r squared times p, and then divided by 4 pi r squared c, where r squared, lowercase r, would be the actual radius of the particle itself. The pi's cancel out, and we have this as being equal to p r squared divided by 4 r squared times c. Now, at this point, we can set the force of the radiation pressure and the force of gravity, we can set them equal to each other and then solve for r. So we can say that p r squared divided by 4 r squared c, this would be equal to 3p over, or rather, my apologies, 4 pi g m rho r cubed divided by 3 r squared. And so at this point, we can say that we notice that r squared, capital R cancels out. So critical radius is not dependent on the distance between the particle and the sun whatsoever. And we're essentially just solving for r. So we can actually, this cubed cancels out, and then this r essentially, and we have r would be equal to 3 times the power output of the sun divided by 16 pi times the gravitational constant times the mass of the sun times the density of the particle itself times the speed of light. So we say if the power output of the sun is constant, the mass of the sun is constant, the gravitational constant is of course a constant, and the speed of light is a constant. The critical radius is mostly dependent on the density of the particle itself. So we can say that this would be the critical radius of the particle, such that it will be anything less than this would be anything less than this, the particle would be blown out of the solar system. This is your answer to part A. For part B, they want you to solve it using a density of 1,000 kilograms per cubic meter. So the critical radius R would be, it would be 3 times the power output of the sun, 3 times 3.90 times 10 to the 26 watts. That would be the power output of the sun, divided by 16 pi, times the gravitational constant, 6.67 times 10 to the negative 11th Newton meters squared per kilogram squared, multiplied by the mass of the sun, 1.99 times 10 to the 30th kilograms, and then times the density of the particle, 1,000 kilograms per cubic meter, and then again multiplied. This would be multiplied by here the speed of light. So 3.00 times 10 to the 8th meters per second. And we find that the critical radius here would be 5.8 times 10 to the negative 7th meters. This would be your answer for part B. However, anything less than that, it would be blown out of the solar system. That is the end of the solution. Thank you for watching.